Okay, the title of my presentation is Can we use principles from musical instruments to fix the Achilles heel of timber floors, impact sound insulation? And this is a little pun actually. I mean, the heel of Achilles is that basically when the heel hits the timber floor, that's the big problem we have identified here in our research. This picture is one of my favorites, and it symbolizes basically what we do all day long as acousticians. The calipers, they can be a symbol for the measurement, whereas the sandwich is the symbol for perception. We can measure the thickness of this sandwich with incredible precision, but that does not tell us whether we will like the taste of the sandwich or not. So we want to find a good tool so that we can extract an objective measurement on this that will describe the perceived annoyance from the sound in a good, reliable way. And regarding timber floors, we're not quite there yet, but we're on the way. Here's a little picture that my wife helped to draw for me that illustrates the characteristic of the problem that I'm talking about. Because timber floors, they tend to have some more low frequency content in their sound when people are walking, running, or bouncing balls on the top floor. These problems, they are present in concrete constructions as well, of course, but they tend to be a bit more loud in the timber house. And we have more than 10 years of research in our and experience on this topic, so we know that this is the case. It's not a disaster, but on the same time, the timber industry often choose to build in a higher sound class. They choose the premium level of acoustics to be certain that they will have satisfied customers in the end. And it's not reasonable that we should use separate yardsticks depending on which construction system we want to build. If we have a value that is good objectively, then we want to make sure that the people are satisfied as well. And this is two typical Swedish living rooms of comparable buildings. Both have the same rated sound insulation. And impact sound insulation is evaluated in a limited frequency range. But as you can see here, the frequency content of the sound is quite different. And even though these two buildings, they have the same rated sound class, but this is what we tend to find out when we follow this up with questionnaire studies and laboratory measurements, that even though the measured sound insulation is exactly the same in both cases, people tend to be slightly less satisfied in the timber buildings. But we want to have impact sound insulation that should be neutral to the construction system. If we have a good value on the decibel scale, then people should be satisfied. And the same thing goes for bad values. So we may need to extend the frequency range to include these lower frequencies down to 20 Hertz perhaps. Because you see, here's where the floors really start to differ. The wooden impact sound levels, they go up, whereas the concrete sound levels go down. And a lot of the energy of the sound from like footsteps, thuds, and jumping, they are precisely in this area. So this is a problem that when we are designing our buildings, we are designing them for the frequency range that might not be the proper one to reflect the perceived annoyance. And when we increase this range and modify the evaluation procedure to include the lower frequencies, we can end up with this. And at the moment there is a very big research project going on in Sweden as well. It's this like part 3, and I've been involved in part 1 and 2. So they're collating a lot of data to get a strong statistical strength in this analysis. So that's the problem that we're dealing with here, because there are also indications that the next revision of the building code in Sweden might include these lower frequencies. And that means that the timber industry, they have to have technical solutions ready because if new requirements are introduced and they don't have a solution, that's going to be a really terrible situation. That means we have to start designing new solutions now so that we're ready in case sharper requirements are introduced. Now, we move on to the main topic of this presentation with musical instruments. We have at present a situation where we don't have the same kind of reliable calculation and prediction tools when designing in wood compared to when we're designing in concrete. We have really good numerical tools to do analysis with. But Tim Elfström, he's a new guy that we recruited in Sweden. He has a background as an architect and a guitar luthier, and he presented this brilliant idea to me, and I really, really liked it. Because luthiers, they have known for 500 years how to refine timber to produce as much sound as possible. They have so much empirical data and trial and errors. For instance, Stradivarius, the really famous violin builder, he was building violins for 70 years before his death. And he knew that if you divide the length of the violin in 72 parts, and you put the bridge on the 33rd of these 72 parts, it's perfect. But now, with modern science, we also know why this is perfect, because we can analyze with the modal analysis to see how this top part of the instrument is moving and how we can modify this. So what if we can do the exact opposite? In theory, this should result in the best possible timber floor. We use the principles from musical instruments, but we do it the other way around instead, to produce as little sound as possible. And here's a sound source that is really common, a loudspeaker. And the loudspeaker is a very efficient sound source. It's light and it is stiff. So when the cone is moving back and forth, it can really move a lot of air. And it's got a soft suspension around the edges, and it's stiff in the middle. And this is basically the same thing that the luthiers try to do with their instruments. And here's a picture of a disassembled guitar. And you see the part with the hole in, that's the one on top. And this is the floor that we're walking on. This is a part that is excited by vibrations from the strings or the foot of the walking persons. And the bottom of the guitar is the ceiling in the floor below. And here we have materials, and we have bracings that carry these plates. So there are quite a lot of similarities here. And the bracing pattern, here's a nice picture from a guitar factory. As you see here, they have been trying a lot of different various constructions on the bracing system and trying to find the best value. But the previous picture I showed you is, I believe, the most common one, because that's the one that produces most sound. But here's a lot of trial and error and mock-ups and things, and this kind of reminds me of how we also work sometimes with timber constructions. We do mock-up buildings and we evaluate them with various solutions because we cannot calculate it. Now towards the high-tech part. Here's it's not a guitar, but it's a sitar, and this guy made a modal analysis using this laser Doppler vibrometer to scan the surface of the sitar when it's excited at the bridge. I think he's holding up a shaker that excites the top plate. And to the right there we have the different eigenfrequencies of the plate. So if we look at let's see if we can also show the mouse pointer, I hope so. The second one in the middle on the top, there we have the first one eigenfrequency, 369 hertz. And this one is really effective to pump a lot of air. And then we have the second one, SB2,1, 612 hertz, where it's moving in two parts longitudinally. And then the third one, it's the cross plane dipole. And from what I've learned about instrument construction, these first three are the critical ones to get a lot of sound. So I suspect this is something we should keep an eye out also on the timber floor. And when we plot all these eigenfrequencies, you can see them as peaks in this mobility diagram down to the left. And this is for the top plate, but we will get different spectrums for the top plate and the bottom plate and the walls and every component. And if these spectrums, if they harmonize together, they will produce much stronger sound. So I think that it might be possible to deharmonize them so that the peaks don't coincide with each other. That should be advantageous with regards to impact sound insulation. Now, next picture here. If you notice the shape of the bracing pattern on this guitar, you have like an X pattern in the middle. And this is basically the same thing as the woofer in the loudspeaker. This is the first big mode where the whole plate is moving back and forth. And that's analogous to the subwoofer element on a loudspeaker. But then we have also here different smaller bracing parts of the plate as well, which with a longitudinal and a cross modal dipole, which could be represented by the middle frequency woofer. And then for the smallest portions could be the tweeter. And this is also where you see it's got like the profile of the Golden Gate Bridge, some of these. This is something you can find on premium instruments, where they have sanded them down and to get the perfect torque and strength curve of the bracing, so that it's going to be maximum stiffness where it should produce most sound. And then toward the edges, it gets thinner and thinner. And just as a loudspeaker, it's like on the really nice instruments, it's leaf thin at the edge. It's actually built on the brink of disaster. And another analogy, I really like analogies. With a choir, you get maximum power when the whole choir sings in tune, when they are harmonized. All the eigenfrequencies of these singers, they coincide and they amplify each other. So this is another way of looking at it. So maybe this guy is the top floor, and this is the short wall, and this is a long wall, and this one is the ceiling. Yeah, you get the picture. We have many components in a building, all with different eigenfrequencies. So as acousticians, we want it to be flexible in the middle and stiff at the edges. That's the inverse of the loudspeaker principle. But I suspect that this might introduce some other issues with strength when we talk to the constructors. So this might be a challenge. And here's another idea I was thinking. If you have a string quartet, they could be represented by the different room types in an apartment. You have small bedrooms, master bedroom, and living room. This is, I believe, the three main groups of room that we can find. And all these have typical eigenfrequency patterns that should probably end up in different groups as well. So we maybe should treat them somewhat differently, would be the optimal solution. We can't change the ceiling height, that's pretty much fixed, but the width and length is something we can vary. And we can also vary the construction of the floor and the ceiling and try to optimize them for their respective use. For instance, you don't walk much in a small bedroom. The walking takes place in the living room primarily. But the small rooms, so you can take one step and maybe you're outside of the room. So maybe it should be another ambition for those ones. Acoustics, we know why and what, but we don't know how. That's why we need help from the other disciplines, how to do it in practice. So our hypothesis here, that is, it is possible to control the modes in the floor and thereby reduce walking sound annoyance. And the first thing is, we know that we can control the modes. This is definitely possible. But we do not know whether the effect is relevant or negligible. So this is something that should be evaluated, perhaps in a research project. That could be really interesting to see. we will get an effect, but maybe the effect isn't that large that it's worthwhile pursuing, but we don't know that yet. So that there is a lot of knowledge within musical acoustics about this stuff. And another example is the stage floor where for an orchestra. That is a floor construction that is an integrated part of the orchestra to produce sound. So that's a type of floor that's made to sound as much as possible. And there are probably some research papers on the optimum stage floor construction as well. So there's a lot of things to look into here. So now we're nearing the end. And if you want to know more, I have this YouTube channel. It's just my name on YouTube, and I try to put up all my stuff there. And hopefully, with the artificial intelligence, I will be able to, in the future, also add more and more subtitles to my clips as well, so that you shouldn't need to know Swedish to follow me. And that's all I had for this presentation. Thank you very much.